So this is the video for the next, just the last part of the differentiation rules that we started in the last video. There will be one additional short video tomorrow to finish up section 2.2. So we learned the constant derivative of a constant was 0. So real quick to recap what you should know already, that if y equals 7, y prime is nothing. And if y equals x to the 6th, then y prime is 6x to the 5th. And if y equals, we have the constant multiple rule, like if y equals 4x squared, the y prime is just 8x. And we learned that if y equals x to the 4th minus 6x squared plus 7, that y prime, we could take the derivative of one term at a time. This was 4x to the 3rd. Move the 2 out front. 2 times 6 is 12x to the 1st, and then the 7 goes away. And then there were a lot of examples where we had to rewrite things with square roots or denominators. So that was kind of where we were. All right. So 3 derivatives left. One is just that it turns out the derivative of the sine of x is in fact the cosine of x. Not going to worry about the proof of that. It just turns out to be true. Need you to trust me on that one. So what that might turn into is if I have y equals 6 sine of x, my derivative, that's just another constant multiple rule. That would just be 6 times the derivative of sine, which is just cosine. This is 6 times the cosine of x. It's allowed to be that simple. Or if I had y equals 3 over x to the 4th minus 7 sine of x. Let's remember that I have to rewrite this first. This is a good review from yesterday. This should be 3x to the negative 4th minus 7 sine of x. Notice I didn't take the derivative yet of that 7 sine of x, because all I was doing was rewriting the first part, and it would be really mathematically wrong to have it. If you took the derivative of that second part, which is just going to be 7 cosine of x, by rewriting the first part, you're not taking the derivative. It's not y prime. It wouldn't be y. So just rewrite it first. I'm not sure why I just did that. Now let's take the derivative. That's a power rule. Move the negative 4 out front. That'd be what? Negative 12. Lower the exponent by 1 to the x to the negative 5th. And now minus 7 cosine of x. Now I might write this as negative 12 over x to the 5th minus 7 cosine of x. So there's the first derivative, that the derivative of sine of x is cosine of x. Next one. The derivative of the cosine of x is negative sine of x. And you can't lose that sign, S-I-G-N. So from here, it's much the same stuff. So y equals 6 cosine of x. Then the derivative of that would be 6 times the negative sine of x. And don't write it like this. I guess it's not wrong. That sure looks like you're saying 6 minus. You're not saying 6 minus. It's 6 times negative sine of x, which would just be negative 6 sine of x. And from there, everything looks like everything else. Okay. And then the third one, we're going to start talking about exponential functions, at least briefly. You may recall that exponential functions and logarithmic functions are inverses. And we'll actually talk about inverse functions in this chapter, and then after that, logarithmic functions. But here we're just looking at the function y equals e to the x. You may remember that e is approximately 2.718, and there's a mathematical story behind where e comes from, but not relevant to today's conversation. You should know that that function, an exponential growth function, looks kind of like this. That's the point 0, 1, because e to the 0th is 1. If I were to label a couple points here just to make it make sense, like right up there, let's see, I'm getting ahead of myself. That's the point 0, 1. This point here would be the point 1, e. If I went further up here, that's not to scale, that would be the point 2, e squared, which is like 7 point something. So that's the function e to the x. it turns out that the derivative, and this is going to seem weird, I promise you it is, but I promise you it's right. Turns out that the derivative of e to the x is e to the x. The derivative of that function is itself, which means what? It's a very unique function in that way. If I were to draw the tangent line right there, just a tangent line, that the slope of that tangent line, that's a derivative, would equal the y value of the function. So if that's the point 1 comma e, not only is the y value e, but the slope of the derivative would also be e, whatever that number is. So this comes in handy, as you might imagine, that the derivative of e to the x is itself. So that turns itself into, what's the derivative of 2e to the x? Well, the derivative of that is just 2e to the x, the constant 2 times the derivative of e to the x, which is just e to the x. Hold on, I'll get a couple more examples here. I can combine with others that we know. If I said y equals x squared plus 3e to the x, the derivative of that would be 2x plus 3e to the x. So just be aware of that. And then the last thing, I'll remind you that what you've been doing so far is finding the derivative. What you've, at least in this section, what some of this next assignment will ask you to do, will also ask you to find the equation of a tangent line. We did that a couple of days ago. You have to find the derivative. You have to evaluate the derivative at the x value. That's the slope. And then use the point slope form to find where the derivative equals 0, or find the equation of the line. So just be aware that some of your homework problems ask you to do that. Okay, that's all I've got for this video. And your assignment, which seems like a lot, but none of these take that long. Your homework here is, we're still on page 143, and you're doing numbers 19 to 24. These are just the same kinds of problems that you did in the last assignment, but now they involve trig functions and e to the x. 19 to 24 and 35 to 38 and 49 to 52. And I think there was one more section that had you, finding some equations, and 55 to 66. So there you have it. See you later.